Assalamualaikum and good morning. This is a video presentation for the simulation assignment of Power System Engineering Group 6 under Dr. Ahmed Safavi. Introduction. The inverse definite minimum time relay or the IDMT relay is an overcurrent relay and was developed to overcome the shortcomings of the standard definite time overcurrent relays. The inverse time is a natural character of an induction type rotating device. If the input current to the device is larger, the speed of rotation of the rotating part of the device also increases. Because of this natural characteristic, this relay is very suitable for overcurrent protection. From figure 1, we can see this is the characteristic of the operating of the IDMT relay. We can see that it is approximately inversely proportional to the fault current. This operating time of the relay is maintained by adjusting the time setting multiplier. The plug setting of the relay is the pickup value of the current and can be adjusted to the required levels in the relays. The plug setting multiplier is the ratio between the actual fault current to the pickup current. The PSM indicates the severity of the fault. The TSM, which is also known as the time dial settings of the relay, is adjusting the tripping mechanism of the relay. The dial is a rotating disc which rotates when fault currents in the relay coil reaches the pickup current. The objectives of our project is first to run a load flow to determine the maximum current at each feeder. Second, run the short circuit analysis to determine the fault current at all buses. Third, select the transformer ratios of the CTs utilizing class 5P CT and suitable accuracy limit current. Fourth, determine the values of the pickup setting and time dial settings of all relays to ensure that the coordinated protection system works properly. Finally, it is to produce the time coordination curves of the relays and confirm the sequence of the relay operation of the relays for three-phase short. We begin with objective 1, which is the load flow analysis. Each group is given a base network with different parameters as shown in the data file. For us, we had to go with set 6 since we are group 6. So we set the bus 1 voltage to 132 and the bus 2 voltage to 33. We also changed the underground cable size and dimensions and also changed the ratings of the induction motors and the load. We also changed the capacity of the T1 and its grounding resistance and also specified the types of relays used. After setting all these parameters into the ETAP, we run the load flow analysis in ETAP. The load flow analysis is done to obtain the maximum load current at each bus. This helps us in determining the load current taken by each relay. As we can see, we have done the load flow analysis and have obtained the maximum load current at each bus. For objective 2, we have to run the short circuit analysis. Since fault can occur at only one time at one bus, we do this bus by bus. So each fault occurs at only one bus. For example, we begin by faulting bus 1 and carrying out the three-phase short circuit. This is done to obtain the fault currents at each bus, which will later help us in determining the time setting of the relay. As we can see, we have obtained the fault currents. After obtaining the fault currents at each bus, namely bus 1, bus 2, bus 3, bus 4 and bus 5, we tabulate the fault currents of the relays in a tabular form. So the third objective is to determine the transformer ratio of the CT. This is done while keeping in mind that the type of CT used is a 5P and it should have a high accuracy limit. The methodology of our project is that the values of the pickup setting and the time dial settings of all relays were determined to ensure a smooth coordinated protection system. The pickup current is calculated is the ratio of the full load current to the CT ratio. The time dial setting can be determined by using the steps as stated. If the fault occurred at the bus, the relay operating time was determined. The RSI value was the full load current. Then the PSM is the ratio of the fault current to the RSI. Then we calculate the R chord, which is 0.14 divided by the PSM value calculated raised to the power 0.02 minus 1. Finally, we calculate the TSM, which is a ratio of the relay operating time and the relay characteristic operating time. The step 4 was skipped after the relay operating time values were set. The parameter needed to be determined in such a case was the real operating time, which is a product of the R chord and the TSM for the relays from the load to the source direction. These steps were then repeated for each bus until the ROT was determined. For the backup current, since each relay has a downstream flow from another relay, we also calculate the backup fault current. This is done by the formula as shown in the slides, where the adjacent relay was operated if the nearest relay failed to operate. The pickup value is shown in the table as calculated, and the RSI values was the full load current of the relay at its bus, also shown in the table below. We calculate the PSM, which is a ratio of the fault current to the RSI, where the fault current used is the same as the fault current at the bus. This is then followed by calculating the RCOT and TSM, and these steps were repeated until the TSM at bus 1 was determined. All the data has been tabulated.
Hello, Assalamu alaikum. My name is Mohammad Jibran, and I am going to explain the D part, which is pickup setting and time setting. So for the pickup setting, we will use this formula, full load current over CT ratio, and this is how we will calculate pickup setting and time setting. And this is the table, which these are the values for all the relays which we want to use for the simulation. And these are the relay, all the calculation for all the relays using the same formula. These are the downstream relay. So these are all the pickup time settings and all the timing settings which we are going to use in the simulation.
So for my part, I will do part E, which is I need to produce the time current coordination curve of the relays on the system. So in order to do that, I need to switch to the star protection coordination, and then I need to switch to star systems, and I will get the time current coordination curve. So from this curve, we can see that relay 13 will operate first, and followed by the relay 10, and then followed by relay 12, and next relay 11, and so on. So the relay system can be said that it is well coordinated because there was good discrimination as the curves does not overlap with each other. From here, we see that it is overlap because relay 13 and relay 10 is parallel. So that's it from my part.
Assalamu alaikum, this is Abdurrahman Hamdi from Group 6. My task is F. So it's confirm the sequence of relay operation of the relay 3-phase short at each bus. So after the design and setting the OCR, my friends set the OCR and everything for the relay. Also making sure the CT ratio is accordingly. And also then for my part we just take the fault and place it on any bus and wait for the sequence. So for us, we received an overload phase thermal, but at time 10 relay 13 operated a phase OC at 50, and then this is the sequence we get when we start the program at bus 1. Similarly, when we started at bus 2, we get the sequence. And that's all for my part. So if you started at any we got the same message and the same sequence. If we started at any bus, we get the same message and sequence: overload phase thermal for relay 10, 11, 12 and 13. And that's all. Thank you.